Before we go on to the next example, let's just kind of go back really quickly and re-examine example 3. Whenever we solve for the particular solution, whenever we solve for our yp, we notice that the g of x here was kind of consisted of a couple fundamental pieces. Part of it, which we labeled y sub p1, looked like a polynomial. It was ax plus b. And then it also kind of looked like it contained terms that would be able to form c e to the 2x plus dx e to the 2x. And it is true that y particular will be the sum of these two pieces. It's y sub p1 plus y sub p2. Now, when we did it in the last video, we went ahead and just kind of put them all together and plugged the whole thing into the differential equation. If you want to, you can actually find these two pieces individually. For example, if I want to find y sub p1, I would need its derivative, which would be a, and then its second derivative would be 0. If I take and substitute that into the differential equation, notice that this is what we would get. We would get 0 minus 2 times y sub p1, which would be a, minus 3 times y, which is ax plus b, and this should be equal to 4x minus 5 plus 6x e to the 2x. And I'm kind of ignoring this piece. I don't want that part to match up. I just want to see like where these two pieces would be equal, because that wouldn't come from anything that would be associated to this. It would be just this portion of g sub x. This would be negative 2a minus 3ax minus 3b, which is equal to 4x minus 5. Again, we would want to kind of go ahead here and equate our coefficients. Negative 2a minus 3b equals 4x minus 5. Setting the equations equal, we get negative 3a equals to 4. Negative 2a minus 3b would be equal to negative 5. And then from there we could, of course, go ahead and solve for a and b. Okay, so that's kind of, in a sense, kind of doing it piecemeal. You're kind of, breaking it apart and doing it step by step, which is perfectly fine. You would want to do the same thing. Then once you solve for a and b, you would get the same values we saw from before. The first equation gives us a equals negative 4/3. Plugging that into the second equation, into this system, the subsystem, then we would also find that b would be equal to, I think it was, 23/9? Yeah, that's right, 23/9. Okay. And then you would do the same thing. You could find y sub p2 by calculating its derivative, its second derivative, plugging it in. And the advantage to this method, if you wanted to do so, is it kind of leads to smaller subsystems, so you don't have quite so much to write. So there is somewhat of a convenience associated to it. I personally don't prefer this. I have no problem, writing as much as needed to create one system that will solve me for all of the undetermined coefficients that go into our ultimate y sub p. So I just wanted to make comment of that's one way you can do it. Let's take a look at the next example. We want to solve the following differential equation. It's y double prime minus 5y prime plus 4y equals 8 e to the x. And the directions in the textbook, and I'll do the same thing too, they say to solve, in this case, they only ask for the particular solution, or find the particular solution. Usually I like to solve them all the way out, but let's just see what they say. Find the particular solution. That is y sub p for this differential equation. So we look at our right-hand side. So this would be like our step 2 normally. And if once we find y complementary, we'd look to try to solve for yp. And we see on the right-hand side that g of x is equal to 8 e to the x. Okay, it's a constant times e to the x. All right, so it makes sense that maybe y particular would be 8 a times e to the x, a constant times e to the x. Let's try out that choice for y sub p and see what happens. We need the derivative. That's also going to be a e to the x. The second derivative is also going to be a e to the x. And now let's go ahead and plug that into the differential equation. Y double prime is a e to the x minus 5 times y prime. That's a e to the x plus 4 times y, which is a e to the x. And this is supposed to be equal to 8 e to the x. A minus 5a plus 4a, if we go ahead and combine those like terms, they actually all cancel out. And so what we end up with is going to be, if I can write it, a contradiction. So a e to the x minus 5a to the x would be negative 4a e to the x, and then the positive 4e to the x, we get 0 equals 8 e to the x, which is a contradiction. So what does that tell us? Well, that tells us that something is not quite right here. Our assumption of the solution of the type a e to the x as being the particular solution doesn't work. Okay. Well, that's very unfortunate because it seemed very reasonable just based upon looking at g of x. It seemed reasonable to expect that that would be a form for the particular solution. To see what's going on here, let's take a step backwards, and I highly advise you should always do this. Again, the directions were to find a particular solution, but I particularly find it helpful just to solve the entire thing. Of course, for WebAssign, for the homework, you do want to follow the direction to plug in the right answer, but let's just solve the whole thing. And really what I want to do is to look at step 1. Let's find our complementary solution, and that's actually going to shed some insight into what's going on here. So let's solve y sub c by solving the related homogeneous differential equation. The auxiliary equation would be m squared minus 5m plus 4 equals to 0. This factors as m minus 4 times m minus 1, which is equal to 0. We get m minus 4 equals to 0. M minus 1 equals to 0, and thus we get two distinct real roots, m equals to 4 and m equals to 1. So the complementary solution in this case is going to be c1 e to the 1x plus c2 e to the 4x. And when you look at the complementary solution, what we see is that a moment ago, we assumed that our particular solution was of this form. We assumed that it was of the form a e to the x. However, that type of term, here I'm calling it c1 e to the x, but we see that it's a solution to the homogeneous linear differential equation, meaning when the right-hand side is set equal to 0. Therefore, that's why we're never going to have that a e to the x term as a solution to the general differential equation, the non-homogeneous one, where we have an a e to the x on the right-hand side. Okay, so this we're going to call, in this section, we're going to refer to this as case 2. So what does that mean? Do we have a particular solution? Does a particular type of solution exist? And the answer is yes. It's not going to be of the form a e to the x, because after all, if you remember back from 4.3 and other discussions, a e to the x and c1 e to the x, those would actually be a pair of linearly dependent functions. Okay. So let me write up here. We know that y sub c is c1 e to the x plus c2 e to the 4x. So what could kind of be closely related to c1 e to the x, but yet still linearly independent? Well, we've seen this before, but what if we were to multiply it by an additional factor of x? In other words, let's assume in this case that y sub p is of the form ax e to the x, and see what happens. So if we calculate yp prime, that would be, again, this is going to be a product rule. It's a e to the x plus ax e to the x. Y double prime of p, derivative of this is just going to be a e to the x plus, here we have another product rule. It's going to be a e to the x plus a x e to the x, which we just combine like terms. That's 2a e to the x plus ax e to the x. If we substitute these, the y sub p and its derivatives into the differential equation, here's what we would get. Y double prime, that's 2a e to the x plus ax e to the x minus 5 times y prime, that's a e to the x plus a to the x, ax e to the x, plus, I'm running out of room here, 4 times y p, which would be ax e to the 4x. This should be equal to 8 e to the x. Let's distribute, get rid of parentheses, a e to the x plus ax e to the x minus 5a e to the x minus 5ax e to the x plus 4ax e to the 4x would be equal to 8x. Okay, let's see what we have here. So, oops. 8e to the x. We have a 2a e to the x, a negative 5a e to the x. Those two are my like terms here. If we combine those, we get negative 3a e to the x, combining the e to the x terms. The x e to the x terms, which would be these ones right here, I'll highlight the coefficients. We have a positive a, and a negative 5a would make negative 4a, but then our plus 4a would cancel, so it would be 0. So we don't have any x e to the 4x term, and so we simply get negative 3a e to the x equals 8 e to the x. Again, think of this as equality of functions. Equate the coefficients. This would say that negative 3a would be equal to 8, and therefore a would be equal to negative 8/3. So we do have a particular solution to this one. It is going to be negative 8/3 x e to the x. So what makes example 4 different than compared to the first 3 examples we saw in section 4.4? The answer is when you solve for your complementary function, right? We solve that first, always. That's always our step 1. And then when we look at step 2, g of x, the thing that we would propose for g of x would have pieces that kind of overlap, or that would already be part of the complementary solution. So those pieces would not be linearly independent. So as we saw previously, if we multiply that, instead of doing e to the x, let's try and shoot for a term of the form x e to the x, which we know then would be linearly independent to e to the x. And sure enough, that does provide us with a particular solution. We can, of course, now go ahead and finish the problem off. If we wanted the general solution to this ODE, it's simply going to be the following. So our general solution is the complementary solution c1 e to the x plus c2 e to the 4x, and then with plus our particular solution, which is negative 8/3 x e to the x. So we'll make a big deal about this. Always solve for the complementary solution first, and then we'll see a little bit later in some of the later examples in this section what to kind of shoot for our y particular in terms of what to assume when it has some overlap or some things in common with the complementary solution. The next thing I want to kind of highlight you to, and this is I'm going to post in D2L, are some of the suggestions. So this is going to be what we call case 1. What happens when there's no kind of overlap between g of x terms, or the pieces of g of x, and our complementary solution? So if you see that g of x, so if the differential equation's right-hand side is just a constant, then assume that the particular solution itself would be a constant. Okay, so if you have like a number 3, 7, or 8, assume that yp of it is going to be a constant. If the right-hand side is a polynomial, so if g of x is a polynomial, then assume y sub p is going to be a polynomial of that degree. So if g of x is a linear polynomial, assume that y sub p is a linear polynomial. If g of x is a quadratic, assume that y sub p is going to be a quadratic, and in particular a general quadratic. So if the polynomial is of degree 2, in the form for yp we would presume you'd want to have every power starting from that highest power all the way down to the constant terms. Similarly, if you had, let's say, a cubic polynomial, then our proposition for y sub p, the particular solution would be like ax cubed plus bx squared plus cx plus e. If we had, let's say, g sub x was like sine of 4x, as we saw in the previous example, we would assume that perhaps we have a particular solution that would have to include both a sine 4x term as well as a cosine 4x term. So our candidate for y sub p in that case would be a cosine 4x plus b sine 4x. Likewise, if you had the cosine of 4x, then you would propose a solution of the type a cosine 4x plus b sine 4x. If we had e to some power, a good candidate for y sub p would be a constant times that power, e to that power. In example 8, so if g of x would see like something of this form, okay, this g of x is roughly as a polynomial times e to that power. This is a linear polynomial times e to the 5x. So we would assume that y sub p would have a comparable form. In other words, we would assume that y sub p would be a to the x plus b times e to the 5x. And same thing here for part 9. If you have like x squared e to the 5x, this is essentially a quadratic times e to a power. So we would assume that y sub p would be like a general quadratic x squared polynomial times e to that power. The 10th example is suppose we had something like e to the 3x times the sine of 4x. So obviously we would assume a constant times something like this, but also we remember that anywhere you have a sine as part of your solution, we assume that we have a cosine term as well. So we'd want to assume not only just an e to the 3x sine 4x term as part of our y sub p, but we would also assume that y sub p could potentially have a e to the 3x cosine of 4x term as well. Okay. And then much like what we saw in 7 and 8, which was a polynomial, or say maybe 7 through 9 you could think of it, a polynomial times e to a power. If we had, let's say, like a polynomial times a trig function, like let's say 5x squared sine of 4x, then you would assume a general quadratic times the sine of 4x, but likewise a general quadratic times the cosine of 4x. And these two polynomials don't have to be the same coefficients. So it would be ax squared plus bx plus c times the cosine of 4x, and then ex squared plus fx plus g times the sine of 4x. And then about as crazy as we're going to get in this section, if you had something like a polynomial times an exponential times a cosine, and again, this could be x squared, x cubed, then it gets really, really long. You get super long systems, things where you would probably end up needing a computer algebra system to solve or a graphing calculator. Probably would end up doing matrices at that point. But the general solution of this form would look like, okay, linear function, we know that's ax plus b. We know we need the e 3 to the x power. And then we also know if we have a cosine or a sine, we need the other. So this would look like ax plus b e to the 3x cosine 4x plus cx plus, I guess the author doesn't know his alphabet, cx plus d e to the 3x sine 4x. And actually, I take that back. That's not, as a joke, there's a reason why they're going from C to E. Okay, and we'll see in the next section when we talk about annihilators. When we start to think about the derivative as a differential operator, usually we'll have that as a D there, and we don't want to mistake that for a coefficient. So this wasn't a typo by any stretch of the imagination. This choice of AB plus CE is kind of made with a little bit of foresight to what we're going to do in the next section. In terms of you solving an individual one, if you set it up, you want to do A, B, C, D, E, F, G, that's perfectly fine. You can go in order. But they're kind of reserving capital D here for what we're going to see next. But this was not a typo. They intentionally went from C to E there.